Hello everyone. On this video we will be looking at continuity at a point. Okay, so let's start off with a visual definition of what a continuous graph looks like. So a continuous function represents an uninterrupted graph. All right, there we go. Okay, so for example, if you have a graph that looks like this, or even a linear function that looks like that, or if you have a graph that looks like this, or if you have a graph that looks like that, those are all continuous functions. Okay, so now a discontinuous function represents a graph with undefined points. Or some other type of interruption. All right, so for example on that one, let's say if you have this same graph, but there's a little hole in it somewhere. Or if you have this same graph, but once again, there's a little hole in it somewhere. Or even if you have a graph that looks like this, where it starts on one side and picks up on the other at two different heights, or an example of a piecewise function. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to the, I guess you could say, the way to find a continuous function of a graph using just the equation and your limits, of course. Okay, so a function is continuous if the following conditions are met. Okay, so you'd use these if you didn't have a graph of your function, but you had the equation. So this is where you use these three conditions. Okay, so your f of c is defined. Okay, so your c could be 1, 2, 3, 4, whatever the suspected discontinuous point is. It has to be defined at that point. I mean, it has to exist. Okay, so 2, the limit of your function as x approaches c exists Remember, for that function to exist, it has to have the same limit from the left and the right approaching c. And the third condition, the limit of f of x as x approaches c equals f of c. All right, so we're going to give a visual of each one of those conditions not being met. All right, so a function is discontinuous if any of the following conditions happen. Okay, so one, what if we have our x and y axis? Or this is your x and this is your y. Let's say you have your graph here, and you have an opening in that graph. Okay, so this is our f of x. And between some interval a and b, there exists a point c. Okay, so that means this point on the graph is our f of c. This point would be our f of a, since that's over a. This point would be our f of b, since it's over b. So that makes this opening our f of c. So since it's an open circle, we know that f of c is not defined. Okay, so this one condition is not met. But we see the other two, the second condition actually is met because the limit of f of x exists. So the limit as x approaches c exists, it just doesn't exist at that point. Okay, now, number two, I'll just put it right next to it. Again, we'll draw our x and y axis. Okay, so what if we have point A and the second part of the interval B, but we have a graph that's a piecewise function, and it picks up like right there. Okay, so for this one, we see that the second one is not met because the limit of f of x does not exist. Remember, the limit of f of x as x approaches c can only exist when the limit approaching c, which is our value right here, is the same from both directions. Here we see the limit approaching c from the left is not the same as the limit of c approaching to the right. They're two different heights on the graph. So we see here that the limit of f of x as x approaches c does not exist. Or just dne. All right. So now we're going to look at the third condition. And again, we're going to go ahead and draw our x and y axis. X and your y. There we go. Okay. And again, we have some interval between A and B where we have a graph the opening inside. But we also have that point there. And at that we will call C. Okay. So we can see here that the limit approaching C to the left and to the right are both the same value. Okay, they're both meeting at the same place. So we see here that the limit of f of x as x approaches C exists, but the limit of f of x as x approaches C does not equal f of C. Okay, because if this is our f of x, if you plug in C, your f of C would have to be on that graph, but your f of C is a different value. Okay, so the limit of f of x does not equal f of C. Okay, if this would have been a continuous function, your limit of f of x would have still been on that graph and it would have equaled the f of C. Okay, so that's when the third condition is not met. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and look at some examples and types of discontinuities. Oops, there we go. Okay, so we have our types of discontinuities. Okay, so our removable discontinuity can be made not necessarily continuous at f of c, but we can make it to where we can figure out what the limit is. Oh, discontinuities can be made continuous at f of c, at least temporarily. To calculate the limit. Okay, so we're not making it continuous overall, we're just making it to the point to where we can find the limit by making the function continuous. Okay, now non-removable discontinuities will remain discontinuous. Okay, that just means that you cannot manipulate that equation in any way to just somehow make it continuous, even temporarily, to find the limit. All right. So let's do a few examples. So what if we discuss the continuity of each function? Okay, so for function A, we have f of x equals 1 over x. Problem B, we have g of x is equal to x squared minus 1 over x minus 1. And for problem C, you have h of x is equal to x squared plus 1 when x is less than or equal to 0. Well, x plus 1. And x squared plus 1 when x is greater than 0. All right, be clean that up a little bit more. That's good enough. All right, so let's go ahead and solve these, or better yet, just discuss them. Okay, so we'll start with problem A. Okay, so we're going to look at f of x equals 1 over x. Okay, so we can see here just by looking at this that we know the denominator can't equal 0. So x can't equal 0. So we know it's discontinuous at 0, because that's the one place where your denominator would be 0, and we can't have that. Okay, so if we look at the graph and get our x and y axis, if we graph this, we'll see that it kind of looks like this, and it goes in that direction. So if we replace x with a value, it'll look like this. If we replace it with a negative value, it'll look like this. Okay. Now there's no way we can maneuver or manipulate this function to somehow, even temporarily, make it continuous to find the limit. So this is what we would call a non-removable. Discontinuity. Okay, so this part of the function is over here, and this part of the function is over here, and we cannot find the limit for those. At least not one limit for each side of it. All right. So let's look at problem B. We have g of x equals x squared minus 1 over x minus 1. Okay. So if you see here, x squared minus 1 is just a difference of squares. You have x squared minus 1 squared. So you can actually factor that numerator out. So you have g of x equals x minus 1 times x plus 1 all over x minus 1. Now, once we do that, these two x minus 1s cancel each other out. So your g of x is going to equal x plus 1, since that's the only thing that didn't cancel out. But just because we canceled it out doesn't mean it's magically going to, be continuous at 1. We still know that x cannot equal 1. So we would be able to find the limit at any point on this graph. We just can't plug in x equals 1 and assume everything's going to be magically better. So this is a removable discontinuity. And let's look at that graph. So we have a graph here. And so we have a negative 1 and 1. This graph will look, you kind of make sure it's a straight line here. and this is over our 1 value. So this is a graph of g of x equals x squared minus 1 over x minus 1, where we would be able to figure out the limit. Really anywhere on this graph. We can even figure out the limit as x approaches 1. Okay. Alright, so if you are still writing, well actually that should be a little taller up, but you get the idea. This would actually be 2. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and go over our problem C. Okay, so, oops. All right, so we have our problem C, which h of x equals x plus 1 when x is less than or equal to 0, and x squared plus 1 when x is greater than 0. All right. So let's go ahead and graph both of those. We can kind of get an idea of our piecewise function. Draw our two x and y axes. So we have our x and our y here, and we have our x and our y there. Now, our x plus 1, that looks like this. H of x equals x plus 1. Our x plus 2, x squared plus 1 will look kind of like that. Oh, that was horrible. Let me redraw that. All right, so that graph looks something like that. That's a little bit better. Still not great, but better than the last one. Okay, and this is our h of x equals x squared plus 1. Okay, so with our piecewise function, what we're going to do is we're going to combine both of these. Okay, so we're going to go ahead and split these up or piece them together. So for x is less than 0, we're going to use x plus 1, well, less than or equal to 0. So that means on this side, which is less than 0, we're going to use this part of the graph. And x squared plus 1 for x is greater than 0, we're going to use this part of the graph, because remember x is greater than 0 on the right side of the y-axis, so we're going to use this part of the graph. Okay, so that's how we have our piecewise function, which is basically combining both sides. H of x equals x plus 1 for x is less than or equal to 0, and x squared plus 1 when x is greater than 0. Okay, now with this one, we see that it's continuous over the entire number line. well, let me make sure, h of x equals x plus 1, x is less than or equal to 0, and x squared plus 1 for x is greater than 0 is continuous. On the entire number line. Okay. All right, so those are a few of the examples explaining continuity and discontinuity. Okay, so hopefully this made sense, and I will see you on the next video.